When an emergency happens, the time required for an ambulance to reach its destination can be a factor determining life and death. Traditionally, sirens are sounded to alert the vehicles on the road of an approaching emergency vehicle. But this method is not very effective when the car windows are closed and the stereo is turned on. This results in delays in making way for the emergency vehicle. To address this problem, an indication more than just a siren is necessary, which will give the car drivers enough time to change the lane. In this video, we can observe how a vehicle-to-vehicle communication system works to alert vehicles in the path of the incoming emergency vehicle. When an ambulance approaches from behind, the cars in front are alerted via vehicle-to-vehicle communication that an emergency vehicle is approaching. This gives them ample time to change the lanes. Thus possible delays and accidents can be avoided. To demonstrate the vehicle-to-vehicle communication using Wi-Fi-P, the tools we used are Sumo, Omnet++, and Vanes. Sumo, which is short for Simulation of Urban Mobility, is a software which can simulate large-scale traffic movement for performance analysis and decision-making. Traffic movements are simulated real-time, as per user-defined scenarios. Custom maps and lanes also can be defined in Sumo. We are using it to simulate on-road traffic and behavior of the ambulance with the other vehicles. Omnet++ is a network simulator which offers simulation for a wide variety of protocols including wireless networks. It is based on C and Eclipse-based IDE. It supports a large number of wired and wireless protocol stacks as well as different model and frameworks. One such framework is Vanes. Vanes is a tool for vehicular network simulation. It connects Sumo and Omnet++ via TCP socket. The wireless nodes are updated in sync with the position of the vehicles. It makes possible to observe the impact of real-time traffic on the nodes. Here, we can see that how the three softwares are related to each other. Both simulators are bidirectionally coupled and simulations are performed online. This way, the influence of vehicular networks on road traffic can be modeled and complex interactions between both domains examined. Vanes contains a large number of simulation models that are applicable to vehicular network simulation in general. The protocol for this communication has been standardized as the Traffic Control Interface. This allows bidirectionally coupled simulation of road traffic and network traffic. This shows how a vehicle on the road in Sumo is mapped to node network traffic in Omnet++. On the left, we can see cars deployed on both the lanes of the road. On the right, the corresponding wireless nodes are communicating with each other using Wi-Fi-P protocol. We can also visualize the packets sent by the nodes. We wanted to achieve vehicle-to-vehicle communication using wireless access in vehicular environments, that is IEEE 802.11p, or Wi-Fi-P. It is an amendment to 802.11a, specifically aimed for V2V communication. It is a support for intelligent transport systems. The newest version of Vanes has a support for this protocol. It uses 5.8 GHz band for communications. The protocol stack for Wi-Fi-P is described by the image. The physical and data link layers are handled by 802.11p, while the application layer contains DSRC. Dedicated short-range communications is a two-way short to medium-range wireless communications capability that permits very high data transmission, which is critical in communications-based active safety applications. Some of the features of DSRC include designated licensed bandwidth, fast network acquisition, low latency, high reliability when required, priority for safety applications, interoperability and security and privacy. It ensures a successful deployment of active safety applications, using widely accepted standards. It supports both V2V and V2I communications. Some of the important parameters of DSRC, which were critical for our application, are WSM and PSID. Provider Service Identifier, or simply PSID, is a unique identifier in Wave Maxib layer. Every allocated PSID represents a unique wave service. A wave service can be conceptualized as any application, protocol, service or higher layer entity that resides above the Wave Short Message Protocol layer. PSID lies in the header of the Wave Short Message, which are transmitted using Wave Short Message Protocol. PSID has mainly three uses as specified in the IEEE wave standards. The first one is identifying the wave service. It is used by the service providers to identify the advertised wave services they provide. Identification is done by the value of PSID in their wave service message header. The second use is to identify the routes to the application. Wave Short Message Protocol uses the PSID set by the sender in its Wave Short Message header. It identifies and discovers the route to the higher layer application that is intended to receive the message. The last use is to identify the permissions. Here, the PSID is also used to identify the permissions of the sender to send certain information. In our application, we used the PSID to differentiate the emergency vehicle from the normal vehicle, which is analogous to the first of the three stated uses. The PSID for an emergency vehicle, as specified in Registration Authority List for PSID, has been set to 133. Whereas, for the normal vehicles, the PSID has been set by default to 0. This is a simulation of our project in OMNET++. The nodes represent the cars. The ambulance is shown by a red symbol. We have implemented separate mat layers for the emergency vehicle and cars. Ambulance broadcasts BSM messages containing its PSID. This message is then received by vehicles in front of the ambulance. On the basis of this PSID, they differentiate the emergency vehicle from the normal vehicle. The PSID for emergency vehicle, as specified in Registration Authority List for PSID, has been set to 133. The received nodes, based on packet received and their current position on the road, change the lane towards right, clearing the leftmost lane beforehand for the incoming ambulance. As we can see, once the ambulance passes by, vehicles return to their normal driving pattern. This is the same simulation in Sumo. All the vehicles on the map have an entry point from where the simulation starts. Various parameters such as car speed, number of vehicles, acceleration and other values can be configured. The ambulance starts at leftmost lane. The scenario depicted here is of dense traffic with 5 vehicles in each lane and in compact formation, that is almost side to side. This makes it difficult for cars to change lanes, as well as to let other vehicles overtake. When the ambulance approaches near other vehicles within 100 meters, they decide whether to change the lane or not. Notice how this vehicle changes its lane. As we can see, once the ambulance passes, vehicles return to their normal driving pattern. Also, the cars traveling on the other side of the road are not affected. This is the time passed since the simulation started. The vehicles calculate the distance between them and the approaching emergency vehicle using coordinates. They also check if they are the intended receiver, that is, are they on the lane on which the emergency vehicle is driving. Concluding this scenario, we saw that the cars successfully managed to free the lane for an approaching ambulance, in spite of heavy traffic. This is the scenario without any V2V emergency vehicle alert system. It depicts the currently existing siren-based alert system. The cars change the lanes only when the ambulance gets near. This results in significant delays for the ambulance. Notice how long it took to get past the fleet of cars. It is more than twice the time taken with emergency vehicle alert system. We can analyze the performance of the system on a number of parameters. One such parameter is ambulance speed with respect to time. The ambulance speed must be high and as constant as possible. Here, in the first graph, the ambulance speed is fairly constant with time. As cars sense the approaching emergency vehicle and change lanes, the ambulance does not slow down. But in the second graph, the ambulance reduces its speed as it arrives near congestion, and accelerates again when the vehicle in front clears the lane for the ambulance. This is because of the fact that the cars take time to change their lanes as they are not aware of the oncoming emergency vehicle. This causes unnecessary delays for the ambulance. Before we go to the next results, let's have a look at the targeted quality of services for our implementation. As directed by SAE International and DSRC Implementation Guide, the quality of services are as shown on the screen. Notably, the message priority is to be set 5 and access category is to be set to 2. These settings essentially change the channel access priority of a node in DSRC. Have a look at priority scheme for Enhanced Distributed Channel Access, or EDCA. In our case, by setting the message priority to a higher value 5 for the emergency vehicle, we have ensured that messages from emergency vehicles get prioritized transmission channel access over other nodes in the network. As a result, we get an improved slot back-off period for emergency vehicle. Slot back-off period is the number of unit time slots a node has to wait for to access the transmission channel. In this graph, we can see the results when the message priority is set to its default value, 1. Note that the slot back-off period for the emergency vehicle is around 450 time slots. Now, we change the message priority of the emergency vehicle to 5. In this graph, we can see that the slot back-off period for the emergency vehicle has almost halved to 250 time slots. Thus, we have ensured a much swifter channel access for an emergency vehicle by setting the message priority higher. Now we analyze the results for latency. Latency is the time taken by a packet to travel from the emergency vehicle to the car nodes in network. We have calculated the maximum average latency and minimum average latency for the duration of our scenario. We found that maximum average latency is around 119 microseconds. Also, the minimum average latency is around 106 microseconds. So, it proves that the latency in our implementation is well within the latency expected in quality of services. In this project, we attempted to show the effectiveness of using WAVE, which is Wi-Fi-P protocol in vehicle-to-vehicle communication. In order to meet the V2V communication requirements such as low latency and reliability, 802.11p amendment was introduced. We showed the advantage of added QoS in form of back-off slots, experienced by the emergency vehicle. The improvement in the speed of the emergency vehicle can prove to be life-saving in emergency situations. This is the group that worked on the project of networked embedded systems. Hrudaynath, J, Chinmay, Shreyas are the master's students at the Eindhoven University of Technology, the Netherlands. Thank you for watching our video.